Hello everyone, welcome back. This week we're going to start chapter 14. It is about multivariable functions. So I'm going to cover the first three sections of chapter 14 today. We start with section 4.1, Introduction to Multivariable Function. 14.1, Multivariable Function. So let's recall what we learned in Calc 1 and Calc 2. We define a function with single variable, so one variable. F of x equal to, say, 3x squared minus 2x plus 1. So it's a quadratic function. Or simply, you write y equal to f of x, right? Or y equal to 3x squared minus 2x plus 1. In here, you see that x is the input, the independent variable, and y is the output of the dependent variable. You plug in x to the function, you got the y value come out. Okay, just one variable, which is x. Okay, one independent variable, just x. All right. Now in Calculus 3, we're going to extend the concept a little bit more. We don't just talk about one variable function. We can have something like f x comma y. For example, 2x squared minus 3xy plus 4y cubed. See, this function have two variables, two independent variables in it, x and y. And since we use x and y in here already, so we call z is the output. Okay, so in here what? We have two inputs, x and y, and we have the output z. And similarly, you can have like 4 or 5 or 6 variable functions. Right? I can have like f of x comma y comma z. And then I use z already. How about w? Z equal to f x y z. Say equal to f times y times z squared, for example. This is squared. Okay? Multivariable function. And what's the idea? So pretty much the very first section, very simple. Trying to introduce to you what it means by multivariable function. A function that have more than one variable. Okay? That's what you learn in Calc 1. Now we extend the concept to function that have more variables, x, y, z, or you may have 4 or 5 variables. All right. Now you get the idea. Let's move on. Talk about some property of this type of function. Let's talk about the graph. So for 2D, right? Fy equal to fx, what you learned in Calc 1. Say the example that I gave you before, the graph is going to be a curve, a line, or a curve in general. Okay? But for z equal to f of x comma y, now you see what? 2 inputs and 1 output. You see that usually the graph is going to be a surface. Could be a curve, could be a line, but in general, we're going to call it a surface. For example, you may have such a thing like a paraboloid. How do I draw it in 3D? You see? It's not just a parabola, it's just a curve, right? Now you see what surface. Right? Like a bowl. Okay? Or you can have something like cone. An example of this one is like z equal to x squared plus y squared, I think. And for cones, I don't remember the formula for the cone. Unless I have this, and this is the cone, okay? 3D cone. And those are the graphs that you see in function of 2 variables and 1 output, right? So multivariable function. We got x, y, z in here. We have 3D object, and then we can have something like omega equal to f of x, y, z, and now this we cannot draw at all. At least I cannot draw it anymore, because if you want to show a graph, this one we need something called 4-dimensional space. We are living in the 3D world, so it's impossible for me to draw. But at least I can show you with 3D x, y, and z. Okay. And that's called the graph. Now, I'm going to talk about something called the, I think it's the book called the level curve. Let me double check on that. Let me keep this graph. Okay, level, this something z equal to x squared plus y squared. And if I put the xy coordinate, it's going to be this. This is for y. This is for x. And then the z coordinate this way. This graph probably like this. Okay, parabola. And let me look for the terminology. Yeah, level curve. We'll use the same thing. Same. Now this one is what? Z equal to x squared plus y squared, right? I have the graph. Now you set z equal to a constant, a value. Say z equal to 5. This means what? 5 is equal to x squared plus y squared. What do we mean by this? Imagine that you're going to cut our paraboloid. You cut your paraboloid at the value of z equal to 5. Say z equal to 5 right here. You cut the paraboloid at this, using a plane that's z equal to 5. The intersection is going to be this circle right here. And that circle is called the level curve. Level curve. So pretty much level curve is the intersection of the graph with a horizontal plane of z equal to some constant. So if I cut at what? Say z equal to 1. See, say 1 is right here, right? Say 1 is right here. I got a circle right here. What if I cut at z equal to 0? Then I only have 1 point. What if I cut at z equal to -1? Then nothing. Okay? You don't have a level curve. Level curve could be a point, could be a curve. In this particular example, the curve is a circle. This one is another circle. Okay? That's called the level curve. And again, you have a level curve whenever you set z, the output, equal to a constant. And z equal to constant is nothing more than a horizontal plane at that value for z. Okay? And pretty much this is the end of 14.1. Now I showed you right here just introduction to multivariable function. The name, I guess, say it all. A function that have several variables as the inputs. Okay? One thing that I haven't mentioned, but I think you guys is capable to do it. Say, go back to the example I'll give you now. X squared y plus y squared, for example, this one. And they ask you, what is z value if you plug in the point 1, comma 2? Very simple, right? Plug in x equal to 1, y equal to 2. You have z. Another point say 0, comma 1. Plug in x equal to 0, y equal to 1. So the input for x is 0, input for y is 1. You plug into the function, you have z. So this is pretty trivial for you guys, I guess. So you can do it yourself. Let me move on to more important stuff for this chapter. I'm going to move on to section 14.2. I'll be talking about limit and continuity. 14.2, limit and continuity. Okay, this is a little bit more complicated than what you've seen in Cut 1 before. Okay, so let's recall what we learned in Cut 1 about limit and continuity for a single variable function. F of x, y equal to f of x. So since this is a recall, so I'm going to go kind of quick. So pretty much you have a graph. Okay, says you have a continuous graph. You see it's continuous, right? So we define what? Limit of f of x when x approaches a equal to L. So a is somewhere in here, okay? This is your x-axis. This is your y-axis. When x getting close to a on either direction from the right or from the left, so x will be right here, x will be right there, and getting close to a. Let's draw it higher. This is y, and this is L. Let me change the marker, make it clearer. So when x approaches a, then what happened? F of x will approach L. The limit f of x equal to L when x approaches a means that when x getting closer to a, then f of x gonna get closer to L. That was the idea. Okay? And this is just for the limit, right? And the graph may be missing some point right there, so it's not continuous, for example. May not be continuous, maybe or maybe not be continuous. That's definition for limit. And then if you have f of a is also equal to L, means what? You have a point right here on the graph. together with those two conditions, and we say that the function is continuous at a point x equal to a. Okay? So continuous means what? If continuous at a point, always say that. If the function continuous at x equal to a, that means you can draw the graph, or you can move a little bit to the left and to the right of the point on the graph. That was graphically the idea of it. Okay? And we have to write down the formal definition for limit so that we can move on to 3D. So we're going to use Cauchy epsilon delta definition. Epsilon delta. It says this. For any, this notation, for any epsilon positive, you can always, this notation means exist, like left word, E, okay? There exists a number delta positive. If you're missing this, then what? Please turn back to, I think it's chapter 4, chapter 5. Let me look, continuity, and the same book, look for cut 1. There exists delta positive such that whenever x minus a is less than delta, means what? X is close to a, then this is notation for them. It implies that f of x minus L will be less than epsilon. And this means whenever x is close to a, then f of x will be close to L. Okay, absolute value means what? The distance, right? X minus a is getting smaller, then the distance from f of x is right here, to L, gonna be smaller as well. That was the idea. It doesn't matter how small you choose the delta, how small you choose the epsilon, I can always find an interval around a, and that distance right here is delta. Okay? That satisfies the condition. And that was the definition that we showed you guys in Calculus 1. Okay, so I assume that you guys took Calc 1 already and you passed this, so you should know the definition. And again, if it's a while ago, please come back and look. Let me check for the chapter. Make sure that you guys get it. It's chapter 2. It's section 2.2. Okay, it's on page 83 in our book. Yes, for your recall of Calc 1 for definition of limit. Precise definition is on 2.4, section 2.4. It's on page 106. Okay, exactly what I wrote in the book. Okay, it's Calc 1, chapter 2, section 2.4, page 106. Is for your reference. This is a review. And we're gonna inherit the same idea when we move on to Calc 3. However, since we're dealing with multivariable function, it's just not limit f of x anymore. We'll be talking about it this way. We're talking about this. Limit f of, say, x comma y, right? And of course, you have more variable x comma y comma z. When not just x approaches a value anymore, now what? X comma y approaches value of a comma b. So think of it like a point on a plane. It's going to be equal to L. Let me try to draw a small graph here and see if that makes sense to you. Too big, smaller. All right. Say I have a curve. Imagine this is the surface, okay? In 3D. And this is the point A in here. X equal to A right here, Y equal to B right here. It's x-axis, y-axis is the x-axis. Okay? When xy approaches the point AB, then the graph gonna approach the point Z right there, up there. This is FAB. See? And for 2D, you see it is 2D. I have a graph right here. I showed you the point A, right? A right here. X can approach A from the left, or X can approach A from the right. For 3D, the point xy can approach the point AB from any direction. Could be in the x direction, could be any this is the y direction or the x direction or any other direction, anywhere. So it's infinitely many ways to approach the point, and that makes the problem a lot harder. But the definition is going to be the same. So first, let me write down the definition of the limit in multivariable function. Then I'll show you how to do the math. Okay. So pretty much the same idea, but we're gonna modify our notation so make it looks better with 3D, make more sense in 3D. Limit of f of x comma y equal to L when x comma y approaches a point A comma B. And again, if you can always any epsilon positive, you can always find delta greater than 0. Now, there's a change, such that for 2D before you have what? X minus A, right? Less than delta, right? Now we don't write x minus A anymore. This is the distance. So how do we write the distance in 2D? The distance from the point xy to the point AB. We call the formula for distance, what was that? Square root x minus A squared plus y minus B squared. Remember? Distance from the point A to the point B, and this is square root, so positive already. It's less than delta, then f of xy minus L will be less than epsilon. So if this happened, then this happened. And usually people don't write this way because it's really inconvenient. We can use vector. Think of it, this is a vector, okay? Called A comma B is like a vector A, for example. And then x comma y is like a vector x. And then xy right here, fxy, you can think of as a vector function, f of vector x. X here stands for x comma y. So now you can rewrite this way, f of x, okay? Limit f of x equal to L when vector x approaches vector A is what? Against epsilon delta, right? And you can write this way, x minus A, you see what I'm writing? Vector x minus vector A, and then you take the magnitude of the vector, it's exactly the same right here, less than delta, then what? F of x minus L, absolute value, less than epsilon. And this is the way that many people prefer to write because it's shorter and it's imply all the cases, not just 2 variables. Because for 3 variables you don't have to x, y, right? So you got function of fx comma y comma z. This part gonna be what? X minus a squared plus y minus b squared plus z minus c squared less than delta. And then 4 variable you have to rewrite with 4 variable. But until a vector use people write this way for multi-variable. And that will work too. Okay. So since this is just a beginning for learning the limit, and then later on continuity means what? You have the point right there, you plug it. There's no hole in it. It's continuous. All right. We tend to give you pretty simple, easy exercise, but I have to claim that in general, if you want to prove, you want to find the limit for multivariable function, it's pretty hard. It's not that simple. And most of the problem, I would say, in our textbook, try to have you to disprove the continuity. Another way, try to show that the function is not continuous. And if you want to prove something that's true in mathematics, you have to prove it true all the time. And if you want to prove something is not true, all you have to do is to find a counter example. Okay? So it's not true all the time because here it's wrong in one case, and therefore the statement is wrong. And that's a lot easier. All right? So to demonstrate that, let me give you a couple examples to show you continuity and limit and no limit or continuity at the point. And let me look for one example. Okay, so your function f x comma y equal to xy over x squared plus y squared, right? It's a two-variable function. Now, they ask you to calculate the limit of xy over x squared plus y squared, limit of that function when xy approaches two variable, okay? Get used to one variable. So x comma y, getting close to where? Close to 0, 0. Ooh, okay, 0, 0. Do we have the limit at that point? Because you plug in, we don't know, but we may have the limit, okay? So, there are many directions to approach 0, 0. Let me draw xy plane, okay? This is the x axis, this is the y axis. Think of the z axis this way, coming out, okay? And this is the point 0, 0. And many line, many curve can approach 0, 0. You can go 0, 0 this way. You can approach the origin 0, 0 that way, or any other way. Get to 0, 0, okay? And if you want to prove that the limit does not exist, all you have to show is what? Limit from one direction give you a different value from the limit from the other direction. And if you don't have the same answer for two directions of going to the same point, then you don't have the limit. That was the idea. So, of course, the easiest way is what? X go to 0 from the direction, so y goes to 0. Try that way. Limit, right? I can write right here. Go to 0, but instead of x, y in general, I can do it 0 comma y. 0 comma y this way. How about? Doesn't matter. X comma 0 means what? I fix y always equal to 0. Y always equal to 0. And x change, this is the line that I have. X approaches 0. Okay? So what happened here if I plug y equal to 0? Y equal to 0. And x changing, right? So y equals 0, top is 0. The bottom is x squared, right? And this is 0 all the time, so this is 0. So far, so good. So y equal to 0. I have the limit equal to 0. Now, I set the line y equal to x. You guys know this line? This is the line I'm talking about right here. This is the bisector. Y equal to x. That line go to 0, 0? Yeah, right? X equals 0, y equals 0. If I have this line right here, then the limit, now what? X comma x, because y now equal to x, equal to y equal to x. I got x squared over x squared plus x squared, which is x squared over 2x squared equal to 1/2. You see? X approaches 0, 0. Okay? So, on one direction right here, the limit is equal to 0. Other direction, another line approach 0, the limit equal to 1/2. And with that, you have two different limits for the same function approach the same point. You say what? The limit does not exist. And this is a very common strategy for you guys to disprove the limit of a multivariable function. You find two different lines, two different curves. You know, this is the line, easy, right? The curve. Like this, the curve. It's hard to write a function. And if you found two different limits for the same function, you say that the limit does not exist. So the answer is limit of f of xy in here when xy approaches 0, 0 does not exist. And this is a very typical example. Okay, you can apply to many other problems. And I claim that, not 100% true, but I claim that many of the exercises, many of the problems you see in this section, 14.2, trying to have you disprove. Okay? Because all you have to do is find a counterexample. But some problems, the limit do exist. Okay, and some problems, the limit do exist. With that, you really have to use definition, and that's make the problem a lot harder for, I guess, many of you guys if you don't quite get the definition of epsilon delta that I've just shown. So it's going to take some time. Please at least watch the video clips or at least read the books on those sections and try to understand. If you have any questions, as usual, more than welcome to ask me right away so I have a chance to help you with. Okay? So let me give you another example with limit exists. Okay. Limit of 3x squared y over x squared plus y squared when x comma y approaches 0, 0. Okay? And how come actually the problem with this problem, the limit does exist. Okay? Let's analyze the problem before we have the answer. So how do you prove that the limit exists? Make a guess. First of all, make a guess. What will be the limit? All right, you try anything. Say plug in y equals 0, x be any, y equals 0, x be any. And if the limit exists, it's got to be equal to 0. Very similar to the first one, right? Or try x equals 0, or try x equal to y. What happened? X equal to y. Then this is what? Try x equal to y. You got what? 3x cubed over x equal to what? 3x squared times x, right? 3x cubed over what? 2x squared. This is 3x, and approach 0, 0 is equal to 0 as x approaches 0. So you test for a couple points, and it seems it agrees that what? Whenever you choose a curve or a line approach 0, 0, that thing actually really go to 0. Okay? So we're going to use a definition. So one more time, we have to write down the definition. Say what? If x, y approaches AB, then what? The function right here, 3x squared y over x squared plus y squared, going to get close to 0. That was the idea. And how you represent this? Well, AB is 0, 0, so write 0, 0 here. So what? X squared minus 0 plus y squared minus 0, and then you take square root, right? Approaches mean less than delta, then 3x squared y over x squared plus y squared less than epsilon. I'm going kind of quick in here. X, y, approach 0, 0 means what? X minus 0 square, right? Plus y minus 0 square, and then you take square root. Really, just x squared, y squared. Okay, less than delta. Then this one, less than epsilon. So how do you prove this? First of all, you have to choose a value for epsilon. So let me see how we choose a value for epsilon that would work. We have to calculate epsilon from here, right? Let's see how we calculate epsilon from here. We have x squared over x squared plus y squared less than 1, okay? So 3y x squared gonna be less than 1 times 3y, which is equal to 3y, okay? And this is gonna be 3y, right? And this 3y gonna be less than, let me see. Oh, okay. 3 square root of y squared, which is less than 3 square root of x squared plus y squared. I'm just showing you the example from the book. I just show you usually there's no rules, and pretty hard for this one. Depends on the problems, and we have different ways to approach. Okay. And this is just what? Delta. So less than